Hi. We are given the the scores from people who have played golf, and then we are to give them, it's kind of a grade, give them a place in the sequence. And in golf, you want to score as low as possible. Now, that's very easy. However, the um, the twist here is that if people score the same, then they need to get the same place, and all the slots that would be taken if they were different are still taken. So then instead, there are certain positions that don't happen, and instead everybody gets the average of what they would have gotten had they been different. So here's some sample scores, and notice here that there are two 68s, and they're given in ascending or non-descending order, and there are three that got 70. So clearly 67 gets first place. Then this would be second and third place, but since they're the same, they have to become the average of that, which is the 2.5 place. So they both need to get 2.5. Then this gets number 4. And this is 5, 6, and 7, which need to share a place. So the average is 5, 6, 7 is 6. And then we get 8 and 9 over here. And there are a lot of different ways that we can uh, attack this problem. So one simple way is that we start by grading. So grading means telling us what position element we should take in order to sort. So here we say, well, first you want the first one, then the second one, then the third one. And since they're all in order already, and since we'd be doing a stable sorting here, then it just becomes really the sequence of indices. So we could actually um, just replace this with indices as well. Here's the length, and then we've computed the indices like this. And that's going to be much faster because we're just generating the indices right away, whereas this actually needs to do comparisons of everything. Okay, now we need to group them. And there are again a couple of different ways we could do this, but since they are already in ascending order and they are non-zero integers, then we could actually just use those values as left argument to the partition function. Partition spelled like this, and that gives us our groups. Because this is exactly how the partition function works. So now we have these groups, some of which only contain a single element. We can take the average of each one, and we can do this with a tacit function. There's a famous spelling, which is the sum divided by the tally. That gives us the average for each one. But we also want repetitions here. So we want to take the shape or the length of each segment and use that to reshape this average. So we take the tally and use it to reshape the average. Now we're back to having groups, but they've been smoothed out. So every value in every group is the same. Now we just need to join them, which we can do with the enlist function. And that gives us our result. In order for this to be a proper function, which we can give a name f, then we wrap it in braces and replace the argument with omega, which is the rightmost letter of the Greek alphabet, so that indicates the right argument. And we can apply that right there. We were doing grouping, and grouping really calls for the key operator. So this is an alternative way of doing things. Let's take the argument here, and we are going to use the key operator. And we're not interested in the actual values. We just want to operate on the indices. So that's the right argument to the operand to key. Keys an operator. It takes this function as operand that applies it in a certain way. And on that, we're going to apply another function, which is going to be pretty much what we had before. The only difference is that key will mix together the results and make it into a single table. That is, every such application here becomes a row, and they might not have the same length, so we can't have that. So we enclose it, and that gives us the same result as before, and then we can enlist it, and we're done. So we can give this the name G. Now, there is a little bit of a complication here, and that is that if we try to apply f on just a single number, that works fine. If we try to apply g on a single number, that gives us a rank error, because key cannot group a scalar. It has no dimensions along which to group them. So we need to amend g a little bit by applying this whole thing that we did, this grouping, to the result of a raveling. So this first makes it into a vector, and then we apply the rest. And now we can do G. Otherwise, it gives the same result. It's only to handle the scalar case. Okay, so this works as well. Now we can go into a completely different way of solving this, and that is, in order for us to get the average positions here, if we go back to just the indices, and let's look at, let's stack this on top of S actually. So we can put S here, and we put the indices here. That gives us a two-element vector, and then we can mix them to make it into rows of a matrix, and that gives us this. So now, if we look at these values, let's look at the 70. We don't actually need to take all the values 5, 6, and 7 in order to get the average. We could just have the smallest value and the largest value, and then add those together and divide them by 2. That would give us the average, because it's a contiguous range of adjacent indices. So, how can we do this? Well, we already looked at how we can get the indices themselves. And we also we can also get the opposite. We did this with grade before, but we also have, so this is grade. We also have a grade that goes the other way, and that wants to sort from the largest to the smallest. So let's stack these on top of each other. And we can actually, let's put in the grade up as well. So we have all three of them. Okay, so here, if you look at the 268s, then this says this is the second largest, and we can see that 8 is the second largest number before 9. So we are going down instead. But of course, we don't want actually to have these large numbers here. We want to go from low to high. So we can reverse the grade. And now we can see how everything lines up except where the numbers are the same. So here's 2 and 3, which is exactly what we need to average, 3 and 2. Over here by 70, again, we have 5, 6, and 7, and we got 7, 6, and 5. So if we are to take the average of these two, that gives us 6. These, of course, give 6 as well, and this gets 6 as well. So that means we can solve this problem by taking the grade of S, or say the indices of X. So these are the indices, and we add them to the reversal of the grade. It gives us double the score. Now we just need to divide it by 2. So we could use parentheses, and do division by 2, but we can also flip the arguments of the division symbol, so it takes what you divide by on the left, and that gives us the result that we want. So we can call this h. And we still have the problem that if you try to apply it on a single number, then the grade will fail. So we can put back in this parenthesis and just put a ravel outside, so this function is applied to the result of this function. And there's one more way that's interesting to look at, and that is self-indices. So if we look for the first occurrence of every number in S itself, so then we can see, let's do the same thing again. Let's stack them on top of each other. We can see what's going on. We can see that we find a 68 in position 2, and this 68 we can also find in position 2 because they're equal to each other. Same thing, all the 70s are found in position 5. There's a different function in APL, which is the interval index. The interval index tries to find the slot wherein a number can fit. So let's say we wanted to find where can we fit in, say, 69 and a half. It says slot 4. 1, 2, 3, 4. We can do this because our number is already sorted, so we can find that slot there. If we do 69 itself, it also says 4. If you do 68, it says 3. So it wants to place, you can see here, it wants to place 1, 2, 3, and a value that's identical to an existing value after the last of those values. Kind of a first come, first serve. And that's very convenient, because now if we use the interval index of S on itself, then we can see that the 68s, with the normal index of, they want to go to the first position, and interval index wants to go to the last position. Same thing here, 5 and 7. Which means the average of the index of and the interval index is going to give us the score that the position that we want. So let's do that. This is pretty neat. How can we make this into a proper standalone function? We could replace all the s's with omegas and wrap it in braces, but there's a neater way. We can make it all tacit by saying that this is a self-application of the index of, and this is a self-application of the interval index, which means we can then apply this. And now we just have some redundant parentheses that we can remove. This is, in my opinion, a beautiful solution. Again, in order to handle a scalar case, we need to ravel. But other than that, this works. Now, it would be interesting to know which solution is the fastest one. Let's import the compare execution facility from the defense workspace. And we probably want to generate some sample numbers as well. So let's say that we are generating 5,000 numbers in the range of 10,000. And so these are the upper limit, and we apply the roll to that to get a whole bunch of numbers. We can take the first 10 and look at them. Okay. Oh, look at that. They're not sorted, so let's sort those. And we can do this by indexing into t with the grade. So this is exactly what grade does. It sorts. Okay. It would also be interesting to know how many unique numbers are actually there. And we can do this by taking the unique mask. So if we try this on the first 10, it indicates with a 1 every time we have a unique number for the first time, and then with a 0 for any duplicates of that, which means that the sum of this is going to be how many unique numbers we have. So this is the plus reduction. We get there are 7 out of these. And what about the whole big collection? So we can see that there are about 4,000 unique numbers out of the 5,000. So there are some duplicates here and there. And they're all in the range 1 to 10,000. Now we can write CMPX, F on T, G on T, H on T, and I on T. And we let it run for a little while. It will apply the functions many times to get an average of the execution speed. That evens out. Oh, look at that. That's a huge difference here. In fact, so much that we can't really tell which one is faster, H and I. So let's try those again. And, well, I guess for this size argument, then H, which was using the grades up and down, was the fastest. We can look at what we've got here. Thank you for watching.